Today we're diving into the foundation of all PLC programming, the bit-level logic instructions that form the building blocks of ladder logic. Every decision a PLC makes ultimately comes down to evaluating whether a condition is true or false, and these bit-level instructions tell the controller exactly how to interpret those states. Up to this point, we've talked about how PLCs process input and output data, and how ladder diagrams represent logic visually. Now we'll connect those ideas by seeing how the PLC interprets individual input bits and uses them to control outputs. Understanding this is critical before we move on to timers, counters, and more advanced control instructions. During today's lecture, we will explain what ladder logic symbols represent in a PLC program, describe how XIC, examine if closed, and XIO, examine if open, instructions operate. And finally, we will interpret how memory bits, ones and zeros, determine whether a rung has logic continuity. The ladder diagram language is a symbolic set of instructions used to create a controller program in a PLC. It uses symbols that represent electrical components and logical operations, allowing programmers to design control logic in a form that closely resembles traditional electrical relay circuits. This visual approach makes it easier for technicians and engineers to interpret and troubleshoot automation systems because the logic flows from left to right, just like current in an electrical schematic. In a ladder diagram, the vertical lines on each side represent power rails, and the horizontal lines between them are called rungs. Each rung represents one logical operation or control statement. The key elements within these rungs are contacts and coils, which are the fundamental symbols used in ladder logic. Contacts represent input conditions, such as push buttons, switches, or sensors, while coils represent output actions, such as energizing a motor, light, or relay. When the correct input conditions are met, the logical path is complete, and the coil symbol at the end of the rung energizes, turning on the output device. Together, these symbolic elements, contacts and coils, form the foundation of PLC ladder programming, translating real-world control functions into logical instructions that the controller can execute. The XIC instruction is used when we want logic to continue only if a certain bit is true. It's functionally equivalent to a normally open contact in relay logic. Each XIC corresponds to a specific memory bit, typically linked to a physical input or an internal relay. When that bit is set to 1, the XIC allows current or logic to pass through its rung. When the bit is 0, the logic path is broken, just like an open switch. This diagram illustrates the operation of the examine if closed or XIC instruction. The XIC instruction is one of the most fundamental elements in ladder logic programming. It functions much like a normally open contact in an electrical circuit, allowing current, or in this case, logical continuity, to pass when its associated bit in the PLC's memory is set to 1, true. In the example shown, the input terminal labeled I1/4 represents a push-button switch. When the button is pressed, the input module detects voltage at that terminal and sets bit 4 in the input image table to 1. The XIC instruction then checks the status of that bit. Because the bit equals 1, the instruction is interpreted as true, which allows the rung to have continuity. The green highlight on the contact indicates that logical flow is active through the instruction. In this true condition, the XIC acts like a closed relay contact, permitting logic to continue to the next instruction on the rung, often an output coil or another logical element. If the bit were 0, false, the contact would open, stopping the logical flow and preventing the rung from energizing its output. This diagram shows how the examine if closed instruction behaves when the associated input bit is off. Here, the input terminal labeled I1/4 represents a push button that is currently released. Since the button is not pressed, no voltage is detected at the input terminal, and the PLC records a logic 0 in bit 4 of the input image table. The XIC instruction checks this bit and finds it to be 0, so it is interpreted as false. Because the instruction is false, the rung behaves as if the contact were open, breaking the logical path and preventing any output coil or instruction to the right from being energized. This behavior directly mirrors a real-world normally open switch. When it is not pressed, the circuit is open and current cannot flow. In ladder logic, the XIC instruction functions the same way. It will only pass logic when the associated input bit is true. In this case, with the input bit at 0, the XIC remains open and stops rung continuity, meaning the PLC will not activate the output connected to this logic path. The examine if open or XIO instruction is essentially the opposite of the XIC. It acts like a normally closed relay contact, allowing logic to pass when its associated bit is 0. The processor examines the bit at the specified address. If the bit is 0, the instruction is true. If it's 1, it's false. XIO is commonly used for stop buttons, limit switches, or safety interlocks that are normally closed and open under fault conditions. This diagram shows how the examine if open instruction functions when the input signal is active. The input terminal labeled I1/4 represents a push button that is currently pressed. When the button is pressed, the input module detects voltage and stores a logic 1 in bit 4 of the input image table. The XIO instruction checks the status of this bit. Because the bit equals 1, the XIO instruction interprets this condition as false. As a result, the logical path through the rung is open, and current does not flow. This behavior mimics the operation of a normally closed contact that opens when the associated device is energized. This diagram illustrates the operation of the examine if open instruction when the input signal is off. The input terminal I1/4 represents a push button connected to the input module. Since the push button is released, no voltage is present at the terminal, and the PLC input module records a logic 0 in bit 4 of the input image table. The XIO instruction then examines the status of this bit. Because the bit equals 0, the XIO instruction is true, and current is allowed to flow through the rung. This behavior corresponds to a normally closed contact that conducts current when its associated device is de-energized. Both XIC and XIO are the core building blocks of PLC ladder logic. They allow the programmer to define the logical relationships that control outputs based on input states. By combining these two simple instructions, we can replicate any Boolean logic function inside the PLC program. The output energize instruction is the final element in a rung that controls a physical device, such as a lamp, motor, or solenoid. It behaves like a relay coil, energized when its rung is true and de-energized when false. When logic continuity exists, the PLC sets the associated output bit to 1. The output module sends voltage to the device. If logic becomes false, the PLC resets that bit to 0 and the device turns off. This diagram illustrates how an output energize instruction operates within a PLC program. In this example, the rung includes two input instructions, I1/1 and I1/4, connected in series. Both inputs must be in the on state for the logic path to be true. In the lower portion of the diagram, both input devices are shown as closed switches, indicating that they are energized. Their corresponding bits in the PLC's input image table are set to 1, establishing a true logical path through the rung. When this occurs, the OT instruction at the end of the rung is executed as true. In the upper portion of the diagram, the OT instruction writes a logic 1 to bit O2/1 in the output image table. This action energizes the output device, represented here by a yellow indicator light, which turns on as a result. The PLC continually scans the inputs, updates the logic, and sets or resets the outputs accordingly. In summary, when all input conditions on a rung are true, the PLC sets the OE instruction to 1, energizing the corresponding output. If any input condition becomes false, the logic path is broken, the OE resets to 0, and the output device turns off. This process forms the foundation of how PLCs control external equipment through logical decision-making. In the next lecture, we will cover branch instructions, which explains how to create parallel logic paths in a ladder diagram. Branch instructions allow multiple input conditions to be evaluated at the same time, similar to parallel circuits in electrical wiring. This enables one or more alternate conditions to turn on the same output. You'll learn how to construct branches, interpret their logic, and understand how they provide flexibility in PLC programming for more complex control applications.